So today we will, we will continue with data pre-processing, and we will revise one more time the definition of inseparable data sets, separable and inseparable data sets. I will share my screen. So separable and inseparable data sets. Separable means we can find a line, a straight line, or a hyperplane, which can separate two different groups or clusters into two different clusters, for example. So linearly separable, it's a property of two sets of points, and these two sets are linearly separable if there exists at least one line in the plane with all the points of the first set on one side of the line and all points of the other set on the other side of the line. And the idea can be generalized to higher dimensional Euclidean spaces. And in this case, we need to replace the straight line with a plane. Inseparable, it's otherwise. So inseparable, it's impossible to find a straight line to separate the classes into two different classes. It's more complex than this, in fact. So we can take an example, X-inclusive OR. X-inclusive OR, it's binary operation, which is very important in computer science, many different applications. It has this truth table. So the output will be 1 when one of the inputs is 1. This is how can we plot it in two-dimensional space. So we have here X1, we have here X2, for example, or X and Y. So it will look like this one. We need to build a model to classify it. We can use a perceptron, but if we use the perceptron, we know that each perceptron will generate a straight line. So in this case, if we draw a line here, I have a problem in my so plotting a line here will not help us to classify it into two different groups. It's not one line. Maybe we need two lines. It's possible to do it by two lines. So if we can use two perceptrons, for example, so in this case, each perceptron will generate one line, correct? So as you can see here in this decision boundary graph, we have in the middle one class, and above this line it will be 0, and below it will be 0. So how can we do this? We can do this maybe using two perceptrons, for example, or there are many ways to deal with this kind of problems, but you just need to remember that only one decision line will not be able to solve this kind of problems. And this is the this one, it's a confusion matrix. And if you can see here, 2 from class 0 was classified as 0, 2 from class 1 as classified as 1. So the accuracy it's 100%. How can we solve this problem? I got this problem from one of your colleagues. He sent it to me last week, and he just defined X and Y, and he want to use MLB classifier. In fact, we need to use logistic regression model for solving this problem. So we use the MLB classifier, and when we use MLB classifier, it's a neural network. In fact, it's a neural network. MLB classifier, it's a neural network, but it's a very simple one. It has two inputs because the inputs here it's X and Y, correct? From this one, we have two inputs, X and Y. We have 4 data points. The output will be just a binary classification. It's a 0 and 1. So in this case, if you can draw this one, it's a simple neural network which has 2 inputs, and it has only one hidden layer. And in this hidden layer, we have 2 perceptrons or 2 units. We will use this kind of activation function. We will use this kind of solver, for example. You can just do whatever you want. And after that, we will fit the model into our data, and we will predict the output. We will print the coefficient of the model, right? The coefficient here, it will be the weights or number of trainable parameters. For the first, from the first hidden layer to the input, we will have 4 weights and 2 bias. For the output, it will be 2 times 2, so it will be 2 times 2 weights plus 2 bias. So in total, we will have 8 weights and 2 bias and 4 bias values. This is the prediction error. So the prediction error, it will be the number of cases which are not equal, right? We can get it using this one, and we can plot the decision line. It's in 2-dimensional space. So we don't have a straight line, in fact. So we need to plot the decision line using a grid. So we will generate values for X1. Of course, X1 and X2, they are in the same range. So I will generate this mesh grid. and I will run the model to predict each point in which class it belongs to, and plot the contour. And finally, we will get the confusion matrix. So it's in here in GitHub, it's XOR MLB classifier if you want to run it. So if we need to run this one, okay, so we have the code. If you can plot it, it will be great. So if you can plot, so we have this code, right? For XOR, I mean XOR, it's a very complex problem, and you don't imagine. I mean, it's four points, but it's non-separable. It's non-separable. So how can we solve it? You cannot solve it using a perceptron. I mean, usually in my bachelor course, I have this exam to students. The exam is oral, so each time I just give them this question. I plot this XOR, and I ask them to solve it using a perceptron. In fact, we can solve it using a perceptron, but I will let it for you to discover how can do it. So now we used the multi-layer perceptron for solving this problem, and it's quite simple. It just has one hidden layer, and the hidden layer has two neurons. In the output layer, we have two outputs because we have two classes, 0 class and 1 class, right? We use the MLB classifier from Scalab, right? You see it here. Maybe you need to open it in Colab. So we need to run that part first. After that, we need to run this part. So this is my data set. We will use MLB classifier with those conditions. We need to find the predictions. This one is not correct. It's why predict, right? Finally, we can, each time you will get different, in fact, a different solution. Of course, this solution is bad. It's 50% is accuracy here, it's 50%. So this one is not correct. We need to run it one more time. Now we got also, it's 25% error, right? We can run it one more time. So this time we got good solution. It's 100% accuracy, right? So this is the prediction 0110. I used here the whole data set for retraining. This is the coefficient of the model. 1, 2, 3, 4. To bias, maybe we need to check those coefficients. How can we print it? Because we are not printing all coefficient at the moment. Maybe this is for one of the layers, not for the two layers. So we need to use this. I mean, if you want, we can use this random state. So in this case, we can generate the same, we can reproduce the solution. Now we stuck here. So we need to yeah, what I mean, but in fact, we can just train the model for more iterations until we got a good solution. So the solution also, it's not good. If you run it again and again, you will get the same solution, in fact. So maybe we need to change the learning rate, maybe number of epochs. The same problem. Maybe you need to change this one. It is stochastic gradient descent. Yeah. Another So we have this solution, we can just reproduce. Now we have this solution and we have those coefficients. And I mean, the prediction error now it's a 0. This is the confusion matrix. So this example, it's a very simple one. But if you need to plot the neural network, how the neural network look like here, we have two inputs. We have one hidden layer with 2 units, and we have an output layer. And the output layer has, I mean, it's only, I mean, the number should be between 0 and 1, in fact. So it has only one output, correct? So in fact, it looks like, I have a problem at the moment because my, yes, if I need to annotate, my system is not working today. I'm so sorry for this. But if you want to plot, if we need to plot it, it will be, I don't know, it's not working today. I'm so sorry. So I can try to plot it in. So in fact, it's we have two neurons. Oh, sorry, we have two here. We have two inputs, x1 and x2, correct? And we have one here. So this is how it will look like. It will look like this one. So we have this one connected here. This one is connected here. This one is connecting here. So this is the neural network which we have been selecting, right? And the output, we have only one output. We didn't use one hot encoding. If you want, in this case, the output will be 2, but we didn't use one hot encoding. So the output is categorical. So the output here, it will be 0 or it will be 1, right? So we have here a bias. We have here a bias. We have here bias value, correct? So how many weights value? 1, 2, 3, 4, 5, 6. We have 6 omega. So we should have omega 1 until omega 6. For the bias also, we have here, maybe it's P1, we have here P2, and we have here P3. So this is the number of parameters which we have here. So if you are doing it in Keras, for example, and you use model.summary, you will get those number of trainable parameters. We will have here 2 times 2 plus 2. So number of parameters here in that part, it will be 2 times 2 because we have 2 weights. So it will be 2 times 2 plus 2 plus 2 bias. Here it will be 2 times 1 times 2, 1 times 2 plus 1. So this is the number of parameters which we need to get. So okay, so I guess it's a simple one. You have the code. If you want to check the code, you can just go for it. Okay. So we can go back to yes. Yes, so this is the XOR. XOR, it's a very important problem because it's non-separable. And now we have the code which can be used for solving it. I have also another example. How can we generate a data set which looks like XOR? How can we generate a data set which looks like XOR? This one, it's just XOR, which is simple, but now we generate these data points. If you can go back here, this is 1 class, this is 0 class. So, so now we need to generate a data set which looks like XOR. How can we do this? We can just use this simple code. So I'm selecting k equal 100 points. So in fact, I'm selecting 100 points in each class. right? And you are just generating it using this one. So this one, it looks like XOR. So we have two classes. Maybe this is 0, this is 0, this is 1, 0 is 1, or vice versa, for example, right? So this is how we generate the data points. And after that, I need to use MLB also. So I want to use MLB for classifying it. So now we try to make it more complex, right? We try to make it more complex. And I want, I mean, last time we just used 4 points. Now we are generating a data set which looks like XOR. You cannot see the current slide, okay? Can you see it now? Okay, so we have been working with XOR problem, but we need to generate a data which looks like XOR problem. So I call it XOR like. I generated this data point using this piece of code. And after that, I will use the same model for classifying it. Now it's more complex, right? I mean, the other one, it was possible to solve it using a simple MLP with one hidden layer. And in this hidden layer, we have 2 perceptrons. So in total, I have 3 units, 3 neurons connected together to solve this problem. When we make it complex like this one, it will be impossible to find a straight line to solve this problem. We need to find more complex decision boundary. How to generate this complex decision boundary? Using MLB, which is more complex. So now I just used one hidden layer, but using 20 neurons in the hidden layer. So it is the same code, no difference, but I'm applying the new data point in the same example, but now I'm selecting more neurons in the hidden layer. I'm selecting 20. And when we are selecting 20, it will generate really very complex decision boundary like this one. So if you can look into it, now it looks more complex. Do you see? So now I have two classes. We are successfully able to classify it into 2 classes, but using this complex decision boundary. And if you run it several times, each time you will get different solution also. And the accuracy is 100%. So the accuracy is 100%. So I just want you to go to this code in GitHub, XOR MLB classifier. This is XOR, and they try to generate XOR-like dataset and apply it to the same model. Right? Apply it to the same classifier, and we need to generate more complex. And also you can control the overlap here. In fact, I'm selecting Q equal 0.6. It's the offset between classes. You can make it shorter, for example. You can make it 0.2. So you will have some kind of, we can find some kind of overlap, or if you put it equal 0, for example, it will be just, close to each other. Points will be close to each other. So it will be more challenging for the model. So please go to the code in GitHub for this XOR and try to generate this XOR-like dataset. Because we have 6 minutes more, so you can go to the code in 2 minutes or so, and try to generate this one XOR-like, and try to apply the same model for this one, and try to find a system which can classify it into two different classes. We have positive class and negative class, or just 0 and 1, similar to the XOR dataset. You should get results like this one. You should get results like this one. I want to ask you also if you have one hot encoding, and if we need to convert it back into label encoding, how can you do it? So it's just a question to everyone. If you can answer it, please send me your answer. So how can, so we have been working with MNIST, for example, and in MNIST we convert it from label encoding. We convert it from label encoding into one hot encoding. How can we do the opposite? If we need to do the opposite, how can we do it? Right? So we need to know how to convert one hot encoding back into label encoding. in the next slide also, I'm using the XOR using higher order features. I try to make it simple. So this is the answer of the question, which usually I give it to bachelor students. I just ask them, you have XOR dataset, and we need to use a perceptron for classifying it. So how can we do this? Yes, we can do this. In fact, we can do this, but using higher order features. If you can use higher order features, it's feature construction. If you can find a super feature which can help you to, separate the data sets using a straight line, it's a big achievement, in fact. So in the next slide here, we have XOR using higher order feature. So now instead of using X1, instead of plotting it using X1 and X2, this plot, I'm plotting here X1 and X2, just using X1 and X2, right? But if you can plot it as follows, X1 against X1 times X2, it will look like this one, right? And now it's separable using a straight line. So the blue line here, in fact, so the blue line here, it's the decision line which we generated using a perceptron. I solved it here, in fact, using a perceptron in this snapshot. So if you look into this snapshot here, I used a perceptron for solving this very complex problem. So it should be possible, but we need to use higher order features. When we use higher order features, we make life much easier. And this is the idea behind the pre-processing. When you are working with pre-processing, we try first to visualize the data, and after visualizing it, we can find a way for, simplifying it. We can build a simple model. Why should we build a complex model if we can do it simply? Yes, correct. Yes, correct. Yeah. Yes, Muhammad. Yeah. But do it for a vector, for example. So you have a Y train, for example. So you have Y train. Do you see those Y train? It's a vector. So please convert it into label encoding. Yes, as a vector. In one of the examples, you can use it for this MNIST dataset, the example which we see before. If we need to convert it back into, because it will be like a vector of elements, and I need to convert it into a label. So how can we do this? I can give you a hint. So the example which we have now, it's XOR problem, and the XOR problem, it's linearly inseparable, correct? We cannot find a straight line to, if I selected a straight line like this one, the accuracy would be 50%. If I selected a line like, I don't know, it's impossible. It's hard. And the only way for solving it is to find a complex plane like this one. This is complex. This is very complex, correct? And how many parameters here? I used the hidden layer, which has 20 units. So it's 20 times 2, 40, plus 2. So it's 42 plus 3, so it's 45. So in fact, this model, to generate this complex model, to generate this complex decision boundary, we need 45 weights. I need a model with 45 weights. But if you can work a little bit on data pre-processing, and if you can try higher order features, what happened here? We used a perceptron, and the perceptron here, in fact, it has only 2 weights plus 1 bias. So we have 3 parameters. So can you imagine how much reduction in complexity? So I solved the same problem using a model with 3 parameters, but here we solved the same problem using a model with 45 parameters. And remember, when you increase the number of parameters, you need more data for training your model. The chances to overfit will be really very high. So chances to overfit will be very, very high. So feature selection and how can we feature construction? How can we construct features using existing features? In fact, in this problem, I have 2 features. I have X1 and X2, and we try to create new features using the interaction between features. Multiplying X1 and X2, this is the interaction. We consider interaction between X1 and X2. So we created a superior feature, which helped us, in fact, to classify this complex data set using a perceptron, right? So feature construction is very, very important. There are lots of techniques for feature constructions. We need to, you need to read, in fact, and but this simple example, in fact, will show you how important feature construction, how it is important to generate super features which can help you to solve your problems. So now we are finishing today. I will just show you the home assignment. We will go back to this lecture next week. But I mean, we have here the home assignment. So the home assignment will be car plates recognition. We need to recognize the car plates, maybe the car model and the car color. So, and you need to collect your data set or search for a data set online, search for a data set, or really just use your mobile camera and try to collect your own data set. So now we are building the project from scratch. Try to, I mean, to see how you will use it, how you will do it, for example, if you need to use some transfer learning approaches and so on. And we will meet again next week. And please, if you have any questions or comments, just send it to me. And next week, I mean, we will finish this slide, and also we will try to implement error bag propagation from scratch. So we will explain the concept behind the error bag propagation, and also we will implement it from scratch, and we will apply it for a simple problem. So thank you very much for today, and looking forward to meet you again next week. Thank you very much. Bye-bye.